Now that we know what an earthquake is, where it forms, what it's caused by, and the different waves within an earthquake, we're going to look at how we locate an earthquake. So once an earthquake happens, there's a couple of things that scientists can do in order to figure out where exactly that earthquake originated from. Because you can have an earthquake occur in one place and you can feel it from a different state if it's depending on the severity of the earthquake, if it's a far-reaching one or not. So what a scientist will do, or a seismologist, is they will measure the P waves and the S waves. So they have their seismograph, the tool, that took a recording of it, the seismogram, and so the scientists can look at that seismogram and they'll look at the P waves and the S waves on that, and what they do is they graph it. Now, you are not going to have to actually graph this. You just kind of need to understand the process. But the first thing that they do is they graph it. So they'll graph the S wave and then they graph the P wave. They then have a little equation thing that talks about the difference between the two, and that gives them a line. And this line is going to be converted into miles. So however many minutes were between the P and S waves shows you about how many miles there were from one another. So they take that little line, which is miles, and they're going to make it a radius of a circle, and they're going to connect 3 different circles, and that's how they're going to get the epicenter. Now I'm going to show you exactly what I'm talking about on the next slide, but for now just know they do a graph, they figure out the little line, and they convert that line into miles. And they're doing that to find the epicenter. That is a big deal. I would put a star next to that because the test always likes to know, do you know the difference between an epicenter and the focus of an earthquake? Well, we know that the epicenter, remember, center of attention, is on the surface. It's above the surface, while the focus is below the surface. So we are just looking where is the epicenter, not the focus. So when we're locating an earthquake, know that we are finding the epicenter, not the focus. Again, that's important. That's why I'm repeating myself. You need at least 3 seismograph stations in order to know, be able to figure this out. You have to have the data from 3 different places in order to locate where the earthquake was. And again, that is what I'm going to show you on this next slide. So how you find it in word form is just you find the difference in the P and S waves. You have to have 3 sets of data, and where they all connect, that's what shows you where the epicenter is. Okay, so let's take a look. So the first thing you're going to do, so say I'm over here in California, and I'm thinking to myself, oh my gosh, there's an earthquake, just because, the whole room's shaking. So there's an earthquake. Well, as a scientist, I'm going to call up the place, or I'll go to the place and I will look at the seismograph, and I will figure out what was the difference in our P and S wave time arrivals, and that's going to give me a radius. That radius is telling me that that earthquake occurred somewhere 700 kilometers from me. Now remember, we always talk about miles, but when you're looking at science, you always use the metric. So that's going to be kilometers. So it's 700 kilometers away. So if it's 700 kilometers away from me, then I know that earthquake could have happened anywhere within this 700 kilometer circle. So that gave me a radius, and I drew a circle. Well, do I know where the earthquake is? No, because that earthquake, all I know is it was 700 kilometers away, so it could have been anywhere on that circle. So in order to find it out, I'm going to call my buddy up in Michigan, and I'm going to go, hey, yo, Bob, y'all got some readings on that earthquake? And he's going to say, sure do. And he will tell me the earthquake told us it was 3,000 kilometers away from us. So they drew their little radius, and they're going to turn that radius into a circle. So now we know that the earthquake happened somewhere along that giant circle. So that tells me where our circle intersects at 2 places. So I know that the earthquake was either the point where it's intersecting north of me, or it's the point that was intersecting south of me, because that's where the 2 sets of data are overlapping. But does that tell me the epicenter of my earthquake? Not yet. I need a third set of data, so that way I can figure out, was it the north area or was it the south area? So then I call my buddy down in Mexico, and I say, hey, what was your data? And they tell me, and they give me a radius, and they draw a circle. And now I can see that all 3 points of the data all intersect right here. So that is where the epicenter of my earthquake was. Not the focus, but the epicenter of my earthquake. I hope that makes sense. So just to do a quick recap, we had 3 seismograph stations data, and they all drew a radius. So my radius was from my P and S waves. That's what gave it to me. I drew my circle. My other buddy scientist, he gave me his radius and drew a circle. That told me 2 locations the earthquake could have been. So I have to call a third scientist, and they give me their radius and circle. And now I see where all 3 points intersect, and that's the location of my epicenter. So let's go ahead and do a brain break. So the way this works is you get your pen or pencil, and don't be crazy with this, okay? You get your pen or pencil, and you'll hold it by the eraser, and your goal is to toss it not high up, just barely toss it, and catch it at the other end. So you're going to hold it by the eraser, and then you'll toss it, and you'll catch it by where the writing point is. Do not throw your pen or pencils high or far or at somebody, okay? Y'all are high schoolers. You should, don't be children with it. Otherwise, you're not going to participate in the brain break. But just toss it, catch it at the other end. And if you get really good at doing that with that one pencil, then put another one in your hand and do both of them at the same time, catching them at the opposite end. So I'll let you pause this video while you attempt your pen flipping brain break. Okay, intensity and magnitude of earthquakes. So we know how to locate them. Now we're going to figure out just how strong the earthquake is. So when you're looking at intensity and magnitude, those are 2 different types of measurements, just as this first bullet is saying. So your 2 different types of measurements, we can measure the intensity of it, or we can measure the magnitude of it. The first thing that we're going to look at is what intensity is. Intensity is simply saying what was the actual amount of the earthquake shaking or the vibration, and we base this off of the damage that was done at that location. Now, this should remind you of tornadoes. Tornadoes are another thing that we measured based on the amount of damage that was done. Because remember, we measure hurricanes based on the wind speed. But this one, we are looking at the damage. So you're going to look at what type of break was in the ground, the cracks that are actually at the fault line, the buildings that were made to fall, that type of stuff. So you have intensity and magnitude. Magnitude will be what we look at next, but for now, intensity, just the amount of shaking or the amount of vibration given off at that particular location. I know you're probably not done writing, so feel free to pause it because I'm going to move on because the slide is just a vocab word, so that's pretty self-explanatory. Okay, magnitude. This is our second type of measurement. Intensity was looking at the damage done by the earthquake. Magnitude is actually going to look at the size of the seismic wave. And when you're looking at the size of the seismic wave, what that basically is telling you is how much energy was actually released. So this is the more technical thing that you're looking at. When you have intensity, you're just like, okay, this was the damage done, so this is, how bad we can say it was. But with magnitude, you're actually looking at the wave itself, and you're measuring that wave, and therefore you can tell just how much energy came out of it, and that's where you're getting that measurement. So that is much more accurate and scientific, which is why we base what I'm going to tell you on the next slide off of magnitude. So, excuse me, we have something called the Richter scale, which I'm sure that you all have heard of. And the only thing you need to write down is what is both bolded and underlined. If it's bolded and underlined, that obviously should tell you that it is very important. But we measure the earthquakes on what we call the Richter scale. So the Richter scale goes from 1 to 10. You don't need to write down the scale. I just wanted to put it up here so you could get an idea of it. But when we're measuring the Richter scale and we say it was a 7 on the Richter scale, we are actually looking at the magnitude, not the intensity. So Richter scale is based on magnitude, not intensity. So you have a bunch of different values. 1 is insignificant. And that could be earthquake that people didn't even really feel. They probably didn't even know it happened. Only maybe a couple people felt it, and then they wondered, was that an earthquake? And then news probably came out and told them that there was a very minor one. Then you've got your noteworthy one at a 6, where you felt it pretty good, and there probably was a little bit of damage. You have 8, far-reaching, so this is going to be one that is going to be felt very, very far away from the earthquake. There was an earthquake, oh goodness, I cannot remember where it was, but a couple years ago, it was not in Greenville, but we could feel the effects of an earthquake that happened in a different state. We could feel it a little bit here. So that was definitely a far-reaching earthquake that occurred. And then you have 10, extraordinary. And that is just going to be absolutely devastating, tons of damage, and all of that stuff. I don't know the last time there was a 10 earthquake anywhere. That would be interesting to look up after notes, but that would be very, 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 very bad, obviously. So with the scales, there is another scale called moment magnitude. Moment magnitude is looking at the actual magnitude of the earthquake, but there's a couple other things that they're going to use in their calculations of it. So they're looking at how much the fault was displaced. Displaced is just talking about the movement. When we looked at those pictures a while ago in the slides, I showed you how sometimes the earthquake happened and part of the road went way up and the other part of the road went down. And that was a good amount of displacement or movement that actually occurred on that fault line. But when they're looking at the displacement that happened on the fault line, they have to have 3 different things in mind. How much movement was there? Was there a lot of movement? Was there just a little bit of movement? Also, what was the area of the surface break? Did it just make one little crack down a line and move along that? Or did it actually break a ton of that surface surrounding it? And then the last thing they're going to look at, which is going to tell a lot, is how strong was the surface that it broke. Think about chalk versus a diamond. When you have different rocks, they have different hardnesses. So chalk is going to be something that you could break very, very easily. So if there was a lot of displacement along a fault line, but you know that the surrounding rock was as soft as chalk, then that's going to tell you, well, it wasn't really all that strong because the rock was very weak. But if you have an area that's granite and that is very, very strong stone, and there was a lot of breakage, then that's going to tell you, wow, this earthquake was really strong because it broke through a stronger rock. So they see how much movement was there, what area actually broke, and then how strong was the rock that was breaking. And that's moment magnitude. Now, I like for you to at least know about moment magnitude, but to be honest, I would focus more on Richter scale. Knowing Richter scale measures the magnitude of the earthquake and the scale from 1 to 10. That would be what I would focus most on when I'm studying. But moment magnitude, in case you ever see it, that's what it is. So let's keep going. Destruction. So these are some of the things that can happen from an earthquake. Obviously, some buildings can be destroyed or damaged based on the seismic vibration. That's going to be the earthquake waves coming out. And what the damage is going to be based on is the intensity and the duration of the vibration. So is it a lot of just really strong vibration for a very short amount of time? Or is it just a little bit of movement on the ground, but for a longer amount of time? Those are going to give you different effects. So the intensity is just going to be how much energy is being released, the strength of it, and the duration, how long the earthquake lasts. Did the earthquake last for 10 seconds or did the earthquake last for 2 minutes? It's going to give you very different very big differences in terms of a building being destroyed. Also, the material the structure was built on. I'm sure you've all heard that a structure stands better if it's built on rock than sand. Well, what your foundation is going to change up how well that building's going to hold. So the foundation is very, very important. But also the design of the structure. If you live in a place that you know is very prone to earthquakes and you are building a skyscraper, then you're probably going to build that building differently, knowing that an earthquake is very likely to happen. So if you're in California or somewhere like Taiwan, China, they have one of the tallest buildings in the world. It's not the tallest, but one of the tallest buildings. And in that structure, they actually have, it's like a stability ball. And I'm going to come back to this slide, so if you're not done writing, don't panic. I'm just showing you a picture and coming right back. This is the building in Taiwan, Taipei, Taiwan. It's very, very, very tall, obviously, because you're showing you a picture of the 91st floor to the right. But that top picture is showing you the size of this ball that they have that's suspended within the middle of the building. And the reason the architects and the engineers built this here was not just for looks, but it's so that when there's an earthquake, if the building sways one way, the weight of this ball will actually sway the opposite way. And so that way, as this earthquake occurs, the building is not going to be likely to fully collapse over, which would obviously kill many, many people. It's going to help stabilize the structure and offset the movement of the earth based on that earthquake. So just wanted to show you that. So the other thing that can happen is something called liquefaction. This is a very interesting thing that occurs, and this is when there's so much vibration in the ground that it actually turns the soil into a liquid. And the reason this happens is because deep within the ground is groundwater. Groundwater is going to, when you have that much shaking from the earth going on, it's basically stirring things up. So it's moving the groundwater around, and it's causing this dry soil to become saturated with water, and it basically turns it into quicksand, or just like a really thick mud that no longer can support buildings. So the shaking of the earth gets groundwater, it mixes it up, causes it to turn into liquid, or makes the soil fluid, and then the buildings will start to sink. And I actually have a little bit of a video that I can show you. So I will let you pause this video while you switch over to the liquefaction video, and then we'll finish up our notes. Okay, quick brain break. So this is my favorite brain break for all of them. So I hope all of you enjoy it and actually try it. So on one hand, maybe your right hand, hold out just your pinky finger. And then on the other hand, your left hand, hold up your thumb. Now switch by putting up your left thumb and your right pinky, or whichever way. So one hand you have the pinky, one hand you have the thumb, and then you switch so you have them on opposite hands. And y'all can pause this video while you attempt it. It's always kind of challenging. We only have a couple more dangers or damages that an earthquake can cause, but one of them is a tsunami. So a tsunami is a seismic sea wave. So this is something that's actually caused by an earthquake that is on the ocean floor. So I know I don't have things bolded, so I'll just underline it. If you want to write seismic sea wave and you understand that means an earth, actually you just need to write this whole thing down. Write the whole thing, because this is a weirdly worded thing that you can often see. So it's displaced vertically. So you have an earthquake that occurs in the ocean. So if you can imagine, and then part of the ocean floor on that fault line actually goes up. That's what we mean by vertically. And when it goes up, it's like it's throwing this wave of energy through the water. And as it throws that wave of energy through the water, that's what creates your tsunami. Now, if you were in the middle of the ocean and a tsunami occurred, then you actually wouldn't even notice the tsunami. It would just be a little bit higher than normal wave that was moving really fast. The wave does not actually get large until it gets to the surface or the shallow part of the ocean. And that's because that wave is no longer going deep within. It has to be forced up. And I will show you a little video on that. But one sign that a tsunami is about to occur, if you're ever at the beach and then all of a sudden the water all starts to go away from the shoreline, like the ocean is draining, then that is your signal to run. Run to the highest place that you can get, because that water is being taken back so that it can come forward as a big tsunami. So as you're finishing writing this up, I'll just go ahead and say this top picture is actually not a tsunami, that's a cloud. But it was up here and I just thought it was kind of cool, so I kept it. But there are certain types of clouds that actually look like a wave, but that's actually not what the tsunami would look like. And then when you're done writing this down, I will let you pause to switch over to the How Tsunami Forms videos. And then I actually have a video of actual tsunamis occurring so you can actually see them. That is very interesting. So go ahead and pause the video and switch to the How They Form video. And then switch to the video of tsunamis. Okay, so some other dangers, the last bit of dangers that occur with an earthquake are landslides and fires. So literally just write landslides and fires. You don't have to write down everything else. We're going to have a unit where we talk about landslides, but basically the vibration of the ground loosens up the land so much that it can cause this mass movement, which is going to be in one of our next units. And then you have fires. So fires are mainly caused by gas lines. Gas is very, very flammable. So when you have your earthquake that is destroying buildings, it's snapping wires causing the gas lines to rupture, and when those two things mix, you can get some very, very large fires. That picture down on the bottom is the smoke that's occurring from major fires that have to do, that was an earthquake way back in the day, I don't remember when, but obviously it's older, in California, and they had major fires based on that. So the last thing, predicting an earthquake. So hold on, my slide will catch up in just 1 second. There we go. So as far as short range predictions go, there is no short range. And that's really all you need to write down. Don't waste your time writing that whole thing down. Just say there is no short range prediction, okay? No short range prediction. They cannot warn you and say an earthquake is going to happen in the next day or so, or everybody get out of the building, there's going to be an earthquake in the next 10 minutes. They can't tell you anything about a short range prediction. There is nothing. Now, with our hurricanes, we know when they are coming days in advance. With tornadoes, we at least know if conditions could create one. And then when there is one, we at least know to take cover. Even if that's only a couple minutes before it gets there. But with the earthquake, we can't tell you that conditions are favorable. We can't tell you that there's going to be one. We just can tell you after it happened how strong it was, and that's it. So there is no way to predict in the short time if there's going to be an earthquake or not, which is a very terrifying thing. Now, are we in danger of having giant earthquakes here in North Carolina? No, there's not an active fault line really close to us. But California, on the other hand, they live on a major transform boundary with a bunch of active faults. So a lot of times, it's when is the big earthquake going to hit them? Because we do have something called a seismic gap. And this has to do with the long-range prediction. We know that earthquakes are repetitive. They occur on fault lines, and the earth is always moving. So because the earth is always moving, that means there will continue to be earthquakes on all fault lines and all plate boundaries. So as those plates are trying to move and trying to move and trying to move, the energy just gets built up for a very long period of time. Now, if you have little bits of earthquakes here and there, that means some of that energy is being released. But like in California, if you have not had a major earthquake in a very, 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 very long time, that means there has been a lot of energy built up, and at some point, that energy is going to snap, and there will be a major earthquake. Now, there was a decent earthquake there that happened, I believe it was this past year, but they say that is not the major earthquake that the scientists expect to happen. You can always look into that more. But seismic gap is just saying, like what we tell with California, you are nearly twice as likely to have a major earthquake in the next 50 years as not. And that's about the only type of prediction that we can have with earthquakes. So that is your only long-range prediction. So that is all for the notes on earthquakes. The very last set of notes that we have to take is going to be on volcanoes, and those are much shorter than the earthquake ones, I promise. So we'll take a couple notes on volcanoes, then you will review, and then you will have your test. That's how this unit will end. Once you are done writing this down, I do have a video of earthquakes occurring that you can watch just to kind of see. Most of them are going to be in Asian areas because of this very active fault line within the ring of fire that these countries are next to. So I will let you end this video and switch over to the videos of earthquakes if you have time.